Most of you must have played the game tug-of-war. The stronger player pulls the rope towards him and wins. This tug-of-war game is played at the atomic scale also. The rules, however, are quite different in the atomic world. Today, we shall explore some of them. Consider a bond between two atoms, A and B. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Remember, the element that pulls the electron pair towards itself is more electronegative. The attraction between a bonding pair of electrons and the nucleus depends on the number of protons in the nucleus, the distance from the nucleus, the number of electrons between the outer electrons and the nucleus. This chart shows changes in electronegativity across period 3. Electronegativity increases across a period. Why does electronegativity increase across a period? Let us understand this by taking the example of two elements from period 3, sodium at the beginning and chlorine towards the end. Think of sodium chloride as if it were covalently bonded. The valence electrons in both sodium and chlorine are in the third shell or M shell. The sodium nucleus has 11 protons, while the chlorine nucleus has 6 more protons in its nucleus. Due to this, the bonded electron pair gets pulled towards chlorine to such an extent that sodium and chloride ions are formed. This chart shows the patterns of electronegativity in groups 1 and 17. Observe that the electronegativity decreases down a group in the periodic table. To understand this trend, let us take the examples of hydrogen fluoride and hydrogen chloride. In the case of fluorine, the bonding electron pair is closer to the nucleus, and the attraction is therefore high. In the case of chlorine, the bonding electron pair is further away from the nucleus, and the attraction is lower. Fluorine is therefore more electronegative than chlorine. In the periodic table, fluorine is the most electronegative element and cesium is the least electronegative. Since electronegativity must always increase towards fluorine, it becomes easy to remember the patterns of electronegativity in the periodic table. Electronegativity is related to ionization energy. The ionization energy is the energy required to completely remove an electron from a gaseous atom or ion. Just like electronegativity, ionization energy also increases across a period and decreases down a group. When you like something, you have an affinity for it. On the atomic scale too, we find that positively charged nuclei have greater affinity for electrons. Electron affinity reflects the ability of an atom to accept an electron. It is the energy change that occurs when an electron is added to a gaseous atom. The stronger the attraction, the more energy is released in the process. Electron affinities are concerned with the formation of negative ions. In the periodic table, electron affinity increases from left to right across the period and decreases as we move down a group. Let us try to understand this trend. As we go down the group, the number of electron shells gradually increases. As a result, the atomic radius increases despite increasing nuclear charge. Owing to this, the incoming electron experiences a lesser pull from the nucleus. The lesser the attraction, the lower is the electron affinity. Electron affinity increases from left to right across the period because of a decrease in atomic size and the increase in nuclear charge. This causes the incoming electron to experience a greater pull from the nucleus, thus giving a higher electron affinity. The electron affinity of atoms with completely filled shells is almost zero. An atom does not accept an electron in its outermost shell if it already has a stable configuration.